So yeah, let's welcome him and some core distributed algorithms.
All right, thanks very much. So as you said, my name is Greg. I work at Red Hat as a principal software engineer and have been on the Ceph project for over a decade now, which at my age is a little scary to think about. Every time I give a talk in Europe, someone tells me that the content they understood was great, but I talk too fast. So if that happens to you, just start waving wildly and I'll slow down. And I'm happy to take questions during the presentation if you raise your hand and I repeat it and answer back, or maybe I'll tell you that you're 3 slides ahead of me and just wait a minute. I assume you all basically know about Ceph, but it's a distributed object storage system. We have 3 daemons, although only 2 of them are 3 principal daemons, although only 2 of them matter today. We have in the middle here the object storage daemons, or OSDs, which are responsible for storing data, serving read and write I/O to clients, and when something happens to the cluster that changes the state, making sure that all the data is located on all the OSDs it's supposed to be, so we maintain our replication and durability guarantees. We have the monitors, which keep track of the other participants in the cluster. They maintain a series of cluster maps. In particular for this talk, the OSD map, which says what OSDs are part of the cluster and whether those OSDs are up or down right now and what their addresses are and things. And then also we have a metadata server, which today doesn't matter, or for this talk doesn't matter at all, but you heard about earlier with Patrick and Jeff and may hear about later. A Rados cluster generally consists of 3 or 5 monitors and a whole bunch of OSDs working together. When we serve writes out of Rados, an application connects to the cluster, which means it goes and talks to the monitors and says, hey, what does the cluster look like? I want to talk to it. And they get their OSD map and other maps describing the state of the system. They say, hey, I want to do a read or I want to do a write to this particular object foo, and they run our magic crush algorithm, which says which OSD is responsible for serving and processing operations on the object foo, and that's called the primary OSD. It sends that write operation to the primary. The primary runs a bunch of validation to make sure the client is allowed to do that. It does some pre-processing. It sends out replication I/O to the other peers or replicas that share that state. And then once the replicas are replied, then it returns to the client. Visually speaking, 1 round trip to the monitor, and then we can do a whole bunch of writes off of that 1 round trip to the monitor. And it looks like this. So for the purposes of this talk, which is about stretch clusters and Ceph, then this is what we mean. We're not talking about big, wide area networks with hundreds of milliseconds of latency stretched around the world. Ceph is designed for a local area network. It expects fast interconnects. But a thing that has become more popular, or that we see more and more often, and that occasionally shows up, and that people certainly ask for, is that they'll have 2 or 3 data centers, pretty close on dark fiber, and so maybe they have 5 milliseconds of ping and fast interconnects. Or they are running in different availability zones inside of an Amazon cloud or some other cloud provider. So we still expect low latency and high ping, but you are split into 2 or 3 data centers or similar things. So the particular risk we're worried about is that you might have an asymmetric network split that's a lot less likely to happen when you're if you were in a single data center, because you probably only have 1 link between each site. And it's become pretty likely that instead of losing like a single rack at a time, you might lose a whole data center. And that data center might represent fully half of the cluster, or certainly a third of it. And losing that much of a Ceph cluster when it's on a local area network is possible, because you might lose a whole power unit that powers the whole thing or half the thing, but the ways in which it happens will be different, and you hope it's less likely. So people can deploy stretch clusters today with 3 data centers. A very simple one. You probably wouldn't really do it with 2 OSDs in each data center, but looking like this. Or they might do it with what they ask for, although we mostly don't encourage them to do, is with 2 data centers and then a third offsite monitor that might be in the cloud or a VM just running somewhere. And the reason that you want 3 is because if you have 2 monitors in one data center and that data center goes down, you can't make any progress. Anything that the monitors are in charge of, they are a Paxos consensus-based system, so making a change to any of the cluster maps requires more than half the monitors to agree. If you have 3, you need 2 of them to agree. If you have 5 monitors, you need 3 of them to agree. So if this happens and you lose your whole data center, then you might have a surviving data center with all of the data still available in it, but you only have 1 monitor. It can't say, oh, hey, there's only 1 data center alive, so just continue with this one. It requires manual administrator intervention. So the big problem, well, when I was asked to make this possible because of some Red Hat product needs with the OpenShift compute storage or container storage that we were talking about last session. So monitors have to elect a leader. That's because they're consensus-based, and so when you send a request to a monitor, you can send it to any of the monitors, but they want to pick one guy who decides what order the operations happen in and who maintains membership. And so all updates go to the leader, and then he distributes those changes out to the other monitors, which are called peons, and I'm talking too fast. Okay, so a request goes to the monitor cluster. If it's a peon or one of the not in charge monitors, they forward it to the leader. That has some interesting consequences in that during an election, everyone talks to everyone else to try and pick a leader. But once an election happens, the leader talks to all of its peons, but the peons don't need to talk to each other. And I've written out the algorithm here. I'm going to go through this really quickly just because I've got a bunch of pictures that will make it much more obvious. So an election starts for some reason. Generally, either a monitor turns on and he sends out and he joins the cluster by starting an election, or else some kind of timeout happens because they have leases over the data that they can serve reads off of. And so for some reason, the monitor goes, I want to start an election, and I'm going to propose to everybody in the system that I become the leader in this new election epoch. And we have an election epoch to make sure that everyone's on the same page and that it's not old messages. And then everything after starting an election is driven by receiving messages from the other peers. When you receive a propose, you can do three things. You can say, hey, that monitor is not in the quorum, and I want to help him get in the quorum. So I'm going to start a new election to help them join. And I'm going to do that by sending out proposals. Or if the sender is a better candidate for leader than me, and the way classically that we decide someone's a better candidate is they have a lower ID number, then we'll defer to them. Or if the sender has a higher ID than us, then we'll say, hey, I should be the leader, and we'll bump the epoch and propose again. And then to win, if we get a deferral message from all of our peers, we win. If we time out the election, but more than half of the peers, including ourselves, have deferred, we win. If we time out otherwise, we start a new election. So visually, we have three monitors here. 1, 2, 3, hooray. They have numbers 0, 1, and 2. And monitor number 1 says, hey, I want to be the leader. It's epoch 1, so maybe they just all turned on. And monitor 2 gets that proposal, and he says, oh, well, you're a better number than me, so sure, you can be the leader. But at the same time that's happening, monitor 0 gets that message and says, no, I'm a better number than you are, so I'm going to bump to epoch number 2 and propose to everybody. And so even though one got a deferral, he also got the propose, and he says, oh, you're better than me, 0, and 2 obviously says, you're better than me. And so 1 and 2 both defer to 0, and 0 becomes the leader and sends out a victory message. So that works great normally. But if you have a net split, very exciting things happen. In this case, they were all running together, and we just got a net split from 0 to 1. And so monitor 1 eventually times out because he's not getting any updates from monitor 0. And he says, hey, I'm going to bump the epoch and propose that I be the leader. And monitor 2 gets that message and says, oh, well, sure, you're a better number than me. You can be the leader. And after, I think, 5 seconds or something, monitor 1 will say, hey, I won because number 2 agreed with me, and so I'm forming a quorum. But it's only 2 of us. It's just monitors 1 and 2. But meanwhile, while that was happening, eventually monitor 0 goes, hey, I haven't heard back from my peons in a while, and I think I should be the leader. So I better run a new election in case one of them died. And so monitor 0 sends out a propose, also with epoch 3, because he only saw epoch 2 and bumped it. And monitor 2 says, oh, hey, I got a monitor that's not in quorum sending me a proposal. I'd better propose an election to make sure that they get in from everybody. And so monitor 2 proposes with epoch 4 that he be the leader, even though he knows he'll lose later. And monitors 1 and 0 both get that proposal from 2 and say, hey, you can't be leader. I've got a better number than you. So they propose back. And they try and propose to each other, but they can't because the network's still broken. And, monitor 2 will get one of their proposals first and agree to them, but then it'll get from the other guy and go, oh, no. And this cycle just repeats. And so you never, ever get a working quorum because the monitors are trying to elect a leader and keep one stable. So this was the first problem that we identified when I was asked to make stretch clusters work. And we came up with a plan. The first part of the plan was make it possible to change the code at all. The election code in Ceph is some of the oldest code in the system. It's from like 2004, written by grad students. And if you've ever read grad student code, it can be really exciting. We were pretty confident in it because it had been stable for a long time, and we run a lot of tests where we do things to the system, and it didn't break. But we actually just saw a new bug like a month and a half ago that was from this, and that the other people assumed was from some of my earlier changes in a regression, and it wasn't. So there were some issues. And one of the things that made it particularly difficult was that the code mixed message passing from monitor A to B and the election logic about what to do with those messages in the same functions. And that made it hard to test and hard to update. And in particular, I wanted to maintain multiple strategies for running elections. I wanted to maintain the classic one we've been using and the new one that I'm about to talk about. And so I decided to split that up into a new election logic function, or sorry, a new election logic class, which would decide what to do when you say, we got to propose, and the message passing elector class that we already had. And then once I made that split, I also wrote unit tests for the election logic class, which was very exciting for me because, if you want to test this in a lab, we need to set, we have a big lab we can use for testing, but it still needs to run for tens of minutes or several hours, and it's hard to create specific scenarios. Whereas in unit tests, I can just poke it directly at the code and run it, and it all runs in line in one process, and we do time step advancement, and it does what I want. And that made it a lot easier to work with. It made it easier to iterate an experiment when I designed an algorithm, because it turns out that I designed an algorithm and the core idea was fine, but I needed a bunch of new invariants that were always true when you're just going by ID numbers, but that you need to make true when you're using more complicated systems. So here's an example of my unit tests, of the unit tests I ended up building. This one is just a demonstration of that thing I showed you graphically before. The function is called blocked connection continues election, and then we pass in an election strategy. So we might pass in the election strategy classic, which is what I named the old one that I talked about, and then we create an election class, and this one has 5 electors or fake monitors in it, and we give it the strategy, which is usually classic, and then we say, hey, we're going to block messages between monitors 0 and 1, and then we're going to turn all the monitors on and have them start going. And then we do this run timestamps function. And this calls into the test harness, and it says, hey, I want you to advance up to 100 time steps. A time step is the amount of time, or when it advances a time step, it calls to every elector and says, hey, you get to advance 1 time step. And they process their incoming messages and then can queue up outgoing messages. And so delivering a message is a 1 time step process. And it'll run up to 100 because if everything becomes stable, then it'll stop advancing time steps if the electors have no timers waiting for something to time out and if they don't have any messages pending. And then here we have a bunch of assertions. So we have this test for is the election stable, meaning that there are no timers. If an election is stable, there are no timers or messages queued. And since in this one we blocked the messages, we expect that they can't resolve, so it will not be a stable election. And we will expect that the quorum has changed recently. So by recently, I doubled the number of timer steps. That's how long a timer lasts, because it takes two time steps for a round trip message. So things time out after 3 time steps, and I just doubled that for how long the quorum can take without changing. And so we say, hey, it didn't finish. But then we unblock the messaging between them, and then we run forward for more time, and we expect that once there's no net split, everything works. And indeed it does. We have a few extra assertions I check here that we want to be really sure that all the leaders, or that all the monitors agree who the leader is. I can't imagine how they wouldn't, but if they somehow managed to segregate into different groups, or one of them lied, then that would be bad. In particular, you might have a thing where, one of them might have a logic bug and agree to 2 different monitors in the same election, or who both take that or something, and that would be bad. And then we also check that they all agree on what the epoch is, because if they all agree on the leader, but some of them think the epoch is 10 steps behind the others, something went wrong. Test harness is about 500 lines. This is one of the simpler tests. In particular, this one, this passes on the classic strategy, but once I fix net splits blocking progress, then this fails, so I don't run this on my new strategy. And my new strategy is called the connectivity strategy. And I said, hey, we want the most connected monitor to win, so we're going to run heartbeats between all the monitors, and try and maintain and try and figure out like how stable they are, and generate scores for them. And these scores are for every connection between pairwise. These scores are this connection is alive and a number representing how alive it has been over the past time period. We have it's not quite the right formula, but we have a half-life of 12 hours by default, and we will ping every 2 seconds, or I think every second. And assuming that ping comes back within a 2-second period, then we say the connection is alive, and it has been alive since the last time we got a ping. And so we increase the score, otherwise we decrease the score and mark the connection is down. And those scores are, and so a monitor maintains scores for all its peers, but they also widely share those scores. So I, as monitor 0, know exactly what the current scores are from me to everyone else, and I have a slightly out-of-date view of what monitor 1 thinks the scores are and what monitor 1 has seen from everyone else. And then when we get a proposed message, instead of looking at the ID number, we look at the total score, and the one with the higher connectivity score wins, and then we still tie break based off of ID number, but that's not super likely once anything has died. We can also specify that monitors are disallowed. So if you have 2 data centers that are close to each other and a tiebreaker monitor far away, you don't really want everything to have to go out to the tiebreaker monitor who might be hundreds of milliseconds away. So we say he's disallowed. His only job is to pick one data center to win. And there's a lot of nuance to that, but that's basically the idea. There's a pull request up for this now. And visually speaking, we got our 3 monitors. They're pinging each other happily, and they're maintaining. I've just got their local scores here, but everyone says everyone's up, and they have a score of 1. If we net split, then after a while, 0 and 1 both say that the other person is down, and they've decreased their scores. But monitor 2 can still talk to everyone, and he says that, and so the monitor 2 scores for everyone else are still high, and everyone's scores for monitor 2 are high. So after a timeout period, monitor 0 and 1 both will propose to monitor 2 because they can't talk to each other. And monitor 2 gets those proposals and runs the number and says, hey, I got a better score than you guys do, so I'm going to propose that I be the leader in epoch 4. And both of those guys say, yes, I agree, you have a better score than me, you can be the leader. And then monitor 2 wins. But if you then go on to disallow monitor 2, and I don't remember if disallowing will cause an election, but we were running before, and then we said, oh, I don't want monitor 2 to be in charge. So we disallow monitor 2, and a new election happens, and if 1 or 0 propose to monitor 2, then monitor 2 will say, hey, I am not allowed to be the leader. And so what it actually does is, if you're disallowed, you just have a score of 0. But he'll say, oh, well, monitors 1 and 0 both have the same score, but I'm going to pick one of them, and monitor 0 is the one I'm going to pick because he's got the lower ID number and there was a tie. Normally, there probably wouldn't actually be a tie just because of timing, and so one of them would win randomly, but whatever. And then after the timeout period, monitor 0 says, hey, I won. I have a quorum of 0 and 2. Keep in mind, though, that while that's happening, even though the quorum is 0 and 2, 1 and 2 are still happily pinging back and forth, and they're and maintaining and changing scores, and those scores are being propagated back out to the world, back to the other monitors through the working connections. And monitor 1 is also like, I'm running. I want to be in a quorum. I'm going to propose to everyone I can see. So he can send out those proposed messages. But in this strategy, when monitor 2 receives a proposed message from an out of quorum peer, he says, "Oh, you are out of quorum," and he'll like run a test, and he'll say, "Oh, well, if I should run an election right now, I would vote for which guy?" And if he would vote for the current leader, if he would vote for the same guy he voted for last time, then he'll just ignore the proposal. If it would change it, then he might respond to one or bump up and say, "Hey, I want a new election." But in this case, he just says, nope, you're not, like, sending a proposal would not change the outcome of where we are right now, so I'm just dropping you. Question.
I have a question. So what happens if instead of the cards let's split, there is an overloaded link with high latency or high packet loss?
So if the question is, what happens if you have an overloaded link with high latency or packet loss, but not a full break? Often an overloaded link with high latency or packet loss will look to Ceph like a completely dead link just because of the amount of traffic we shove through it. So if it keeps serving all the messages quickly enough, then it might stay and we'll have a problem. But eventually we would expect it to get expect that link to get backed up, and the pings will stop happening. Or the pings will stop being replied to quickly enough, and so it will migrate workloads. Well, the monitors will migrate away from letting that one be the leader, and you'll start getting failure reports from OSDs and the monitors and stuff. So if you have a partial failure, Ceph will have a partial detection, and it may be slow for a while, but it's a better state than where we are now. Anyway, going back to the unit testing, now that I have this cool connectivity strategy, we want to test it. And so instead of testing it in the real world, we can just set it up to look the way we want to. So I have the strategy here where the connection tracker is the thing that keeps track of all the scores that everyone sees, and then a connection report is I monitor 0 have these scores for monitors for myself in 1 and 2. And so that's 1, and connection trackers all of them. So we're grabbing out a connection report and directly editing the history as the score, and I guess I didn't change the liveness, and bumping up the version so that this propagates. And we can do this to a bunch of them. And then I disable the pinging between monitors. And what that means is that they'll stop sending the ping messages, so they will not change the scores away from 0.5, so I know exactly what the scores are. And the only time the scores propagate is when they send election messages to each other. All right. Yep. And then I run forward in time with the start all and run the time steps, and then I make sure, hey, we resolved a score we resolved on a leader, and that leader is stable, and the quorum is stable, even though they had disagreeing scores for what each other were. And we've checked that the leaders agree and the epochs agree. So that's that's an example of why I like my unit tests. So with those changes, the monitors are happy in multi-site. You can have them in a cluster. They deal with net splits. They can deal with dropping one of the data centers if we need to for some other reason, like perhaps because of what we're doing with the OSDs. So when a cluster changes in the when an OSD comes up or down or something about the cluster map changes, the OSDs look at that change and they say, hey, do I have any data I'm responsible for now that someone else is supposed to be responsible for? And if that's the case, they send out a notification saying, hey, you're supposed to be primary for this piece of data now. And when you find out you're primary, then you need to make sure you have the newest version of the data. And that means going through the OSD maps and finding the old peers who might have data that you don't. And then you query those peers and ask what version they have. And then if they have newer data, you ask for the update logs and you ask for the updates. Graphically speaking, let's say we have here, in this case, we have 2 OSDs and the one on the left just rebooted or something. So he's got version 5 of the data, and then the one on the right has version 8. So he asks for the version and he gets it back, and he still knows that he's got version 5 with content A, but he knows that there's newer updates. And then he asks for the updates and says, what are they? Probably what this is this is a collection of objects, and so he's asking for which objects changed. And he gets back, oh, it's these ones. And then he says, hey, send me the new data. This is a series of messages because we don't want any of them to be too large, so he might get 2 at a time, and then know that he has 1 left. And then he asks for it again, and he gets it back to get the newest objects. That makes sense, generally speaking? OK. So that's a real simple example. In real life, we generally have 3 copies of all the data. I'm not putting that on the screen because it's harder to draw and harder to show the problems. So we have 3 copies of all the data, but we generally have a minimum size required to go active to serve any reads or writes on the data of 2. And the reason for that is that we're a very consistent system. We notice if we aren't consistent. We notice if we might be inconsistent. And in particular, if we go active with 1 OSD holding the data, and we accept a write, and then that OSD goes away, we've lost data, and we can't get it back. And if you are running a system with 3 copies, and we tell you that 1 OSD died, and now you've lost all your data, and now you can't access your block device, you're going to be really angry at us. Now, the way this works is that the OSDs know the specific version that everything's at. We don't want anyone else to know the exact versions they're at, because that would mean talking to them on every update. But the OSDs know the exact version they're at, and the monitors know that updates were allowed. The reason, we do work to make sure that's the case. And the reason for that is that when someone becomes a new primary, they need to know who to go ask for the data. And so the OSDs report into the monitors, hey, I am going to go active, and so mark down that I'm allowed to make changes. And this is one of the things that we do just to make sure that we can stay absolutely consistent, and so we know who to talk to. So if we have 2 main data centers and 1 offsite tiebreaker monitor model, and this is a really simplified version of it, obviously, but the problem exists even with more complicated setups. So let's say we have data center 1 on the left and data center 2 on the right, and OSDs 1.0 and 1.1 and 2.0 and 2.1, and they're only peering straight across for whatever reason. Then they might all, your cluster's running and everyone's at version 8. But then we lose OSD 2.0, and life is sad, but hey, we still have OSD 1, and so he can keep on serving the writes and everyone can keep making progress. But now we've lost data center 1. And so that's bad because, OSD 1.0 had the newest version of some data that no one else had. And in particular, maybe we get OSD 2.0 back, but we still can't go active and serve reads and writes because he knows, OSD 1 went active, he probably did some I/O and is at a newer version than me. And so even though you had this thing, you built it for data center loss tolerance, it no longer has tolerated data center loss because of just one bad OSD that wasn't up to date. And that makes everybody sad. And there are systems where this is okay. There are storage systems where if you do that to the system, it just won't even notice that you went back in time. And maybe your application won't notice either. And maybe you won't notice either. But maybe your application does notice and things go horribly, horribly wrong. So we don't let that happen. The example I've given you is a toy example, but it's not super unlikely that you have, dozens of OSDs and one of them rebooted because, a server, you were updating a server software or you were upgrading Ceph. And so one OSD was rebooting and it was continuing to process data in the other data center, and then the data center links broke. And so, most of the data is still available, but some of it isn't, and we really need all of it because of the way we distribute virtual block devices and things. So, this is work in progress, what I'm about to start talking about. I'm working on it now. I was hoping to have the pull request up to direct you here, but not quite. Very, very soon. So the design target for our stretch mode is having 2 main data centers and then a 3rd tiebreaker monitor or a 5th tiebreaker monitor somewhere else. And we're going to have 2 copies of the data in each data center. The reason for that being, if we, that's mostly because of what Red Hat supports and what I felt comfortable letting out into the world. We do support 2 copies with min size 1 if you're running on all flash. And so if you lose a data center out of this, you still have 2 copies of all the data, and it is on its own, even with the dead data center, the surviving data center and set of monitors are a supportable configuration if you just cut it down. We restrict the OSD monitor communications so they stay within a data center. By default, the OSDs are allowed to talk to any monitor they want to, but besides the fact that it might be higher latency to go out and talk to someone else, we also want to notice when OSDs are net split from their peers. And so OSDs ping each other just like the monitors do now, and they will report when they can't talk to their peers to try and mark them dead. But if an OSD can talk to any monitor that's in the quorum, he gets to stay alive. And so we don't want a net split between the data centers and for the losing data center to have all its OSDs talking to the tiebreaker monitor because they can reach it and having that tiebreaker monitor keep them alive. That would be bad. So we say OSDs are only allowed to talk to monitors in their data center to stay alive. And then in addition to requiring a minimum number of OSDs to be alive to go active, we say you have to have OSDs from more than one data center or availability zone or whatever. It's a configurable thing. And that means that if we lose an OSD, then it will have to make another copy on the same or by default you'll have 2 in each. So you'll lose an OSD, but we will make sure that we go active with at least 1 OSD from both sides, and probably all 3 of them. And then let's see. Right. So I already went through this. Cool. And so visually, everybody's pinging each other. we lose the old OSD, but everyone keeps, and the cluster keeps running. And in this case, oh no, OSD 1.0 isn't allowed to do anything. So like you have a data unavailability, which is not great. But you can go work and get OSD 2.0 back online. And meanwhile, OSDs 1.1 and 2.1 are updating their data. But then when the links break, we can still, the tiebreaker monitor chooses OSD 2, or sorry, data center 2 side for whatever reason, and they make their own little cluster, and they change the rules to say you are allowed to go active without having OSDs in multiple data centers, and we are disallowing the monitors in data center 1 from becoming the leader. And then we can keep making updates to OSD 2.1, and when OSD 2.0 comes back, he can keep making updates. And life is great, and I have 5 minutes if you guys have questions.
Everybody's stunned, I guess?
So you mentioned there's a half-life of 12 hours. Why did you settle on that number?
It was completely arbitrary. I needed to write a number down. It's configurable, but basically we want to not immediately forget if a connection died, but we also want it to age out because, like, if you reboot the server monitors on, its score will drop, and we want that to age out.
When is this coming out?
The question is when this is coming out, and the answer is it's going to be in before Octopus is released at the end of the month or in March. Or else I'm going to be in a lot of trouble.
If I got it right, you basically suggest to have, if you have 2 data centers, you'd like to have a copy of 4 then instead of 3?
The question was, if you have 2 data centers, I'm suggesting 4 copies instead of 3 copies? Yes, that's correct. So, like I said during the talk, I really want that if you lose a data center, because if you lose a data center, maybe it's temporary, but there's a good chance it's very long term. And so I want the surviving cluster to be supportable on its own. That's, some people may be sad about that. And so in that case, you can run with 3 data centers, which will mostly work, although still might have trouble with net splitting on the OSD side. I'm planning to get to that after the Octopus release. But for the product needs that Red Hat gave me, then that was sufficient. We could go to 4 copies.
So the reason that the ping statistics in the manager are there now in Nautilus is also because of this feature?
The question was if the reason we have ping statistics in the manager Nautilus are because of this feature, and actually, no, it has nothing to do with it. It's just good information to have. Network issues in Ceph, underneath Ceph in general have resulted in a lot of problems that are hard to diagnose. So we want to expose that more carefully and make it more obvious when they're probably an underlying cause of an issue.
The monitors use their own statistics?
So yes, the monitors use their own statistics. I think the ping statistics that you get in the manager are actually just from the OSD heartbeating, although I'm not totally sure about that. So I guess we can plug these into the manager as well, but we don't yet. Someone in the back had a question. Yes?
You mentioned at the beginning 5 milliseconds between the data centers. Is that something you have to arrive at by testing, or is there any rule from below this level possible?
The question was if 5 milliseconds is a hard limit or something that we arrived at by testing, and the answer is I was just 5 milliseconds is sort of it's not completely arbitrary, but it's not a hard limit. It's just that we have run Ceph in a lot of data centers that had latency up to around 2.5 or 3 milliseconds. And 5 milliseconds, when you add up the latencies on doing write IOs, it's not great, but it's sort of in the range of what you may see in a Ceph hard drive-based cluster anyway, so it's plausible. Whereas, if you do 100 milliseconds, then some of your primaries are going to be across your remote link, and your reads are going to be slow, and your writes are 2.5 of those hops or something, and so they're going to be really slow, and everyone's just miserable. So it needs to be, kind of data center-ish. All right. Well, I will be around. Oh.
Just one small thing that came to mind if I saw your slides with this ping thing. So we are running our monitors in a routed environment and just use BFD, so bidirectional forwarding detection is within our OSPF protocol that we use anyway. So I just was wondering why you invent the wheel twice and don't use BFD already out there.
So the question was why I'm talking about having our own pings. And so I'm writing down ping, but it's actually a normal Ceph over-the-wire message that goes through the normal Ceph communication pipeline. It's not a network primitive. And that's on purpose. We want to make sure that the entire stack is working properly, because, you know, if it may be that the monitor is still alive technically, but if it's like got gigabytes worth of data in swap and it can't handle messages, then we want to mark it as not behaving. The question was about Messenger v2, and it is not necessary for this. Although, I mean, you'll have it, and you should run Messenger v2 if you have it, but this is at a higher layer.
We are available for the next Linux distribution, like the PetSan, for example.
I'm sorry?
About the PetSan, it's a Linux distribution that uses Ceph. The features we will available for the next release for PetSan.
The question was about if this will be in a specific Linux distribution, and I have no idea. This is going into the next upstream Ceph release, and distributions will get it when they get it. This has nothing to do with what the clients are, so it's all server side.
Like PetSan.
It's just part of the packages. Yeah.
Okay, we're out of time.
Okay.
Thank you.
Yeah. Thanks all.